Hi, my name is Bernard Zygelman. I'm from the physics department here at UNLV, and I'm going to be talking about a subject that's dear to me, quantum mechanics or quantum theory, something that I've been teaching for over 20 years, and also a significant part of my research involves this subject. So the quantum theory was developed in the period from 1900 to around 1930 in response to deficiencies in classical physics to predict phenomena at the atomic scale. Taken at the Solvay conference circa 1927, the attendees shown here played a significant role in the development of the modern quantum theory. Classical physics forms the bedrock of our understanding of the physical universe at the macroscopic level. It includes disciplines of mechanics, electricity, magnetism, optics, and thermodynamics. This edifice was built over a period spanning several hundred years, from the beginning of the Age of Enlightenment to the dawn of the 20th century. Armed with new tools enabled by advances in classical physics, researchers began to probe at the end of the 19th century the microscopic world. The quantum theory arose out of a necessity to come to terms with new discoveries at the atomic level. Somebody tell me what's wrong with that picture. In its power to predict atomic, molecular, nuclear, and nanoscale phenomena, the quantum theory is wildly successful. It's one of the most successful theories of all time. It forms the basis of much of post-World War II technology. The old adage of knowledge is power could not be made more demonstrable than in the example provided by the applications of the quantum theory. Massive government investment in science after World War II spawned the technologies that are exploited today in places such as Silicon Valley. In my research at UNLV, I used quantum theory to predict the behavior of matter and radiation at the atomic and molecular level. Data my group produces is used in applications that include energy technologies, nanoscience, as well as atmospheric and astrophysics. With collaborators at Harvard, Sweden, and Russia, my group has also used the quantum theory to understand some of the experiments being performed at the CERN laboratory in Switzerland that probed the interaction of matter with antimatter. In recent years, I have concentrated my efforts to understanding quantum behavior at ultra-cold temperatures. Physicists are interested in such extreme environments because quantum effects become enhanced and can be manipulated at the macroscopic level. The components of the first quantum computers must be chilled to temperatures a hairbreadth above absolute zero. Despite the dramatic success of the quantum theory, some of its original proponents were disturbed by its implications concerning the nature of reality. Albert Einstein, who thought more deeply about the quantum theory than its younger architects, was the leading voice in that criticism. One of the weird aspects of the quantum theories is its reliance on the notion of superposition. Imagine flipping a coin. We expect that it exists either in a head or a tail state, regardless of our lack of knowledge of while it is in the air. In the quantum theory, however, this coin could be simultaneously in a head and tail state at the same time. Erwin Schrödinger ridiculed some of the features of the quantum theory by introducing the famous example of Schrödinger's cat. Schrödinger was so disgusted by the Copenhagen interpretation of quantum theory that he abandoned quantum physics and became an inspirational figure in the nascent field of molecular biology. The 2012 Nobel Prize went to two researchers who directly demonstrated the ability of matter to be in two states at once. Today, researchers are able to create Schrödinger cat-like superpositions in larger molecules, as well as macroscopic devices. Unlike his cat, today Schrödinger, according to the Copenhagen interpretation, is in a definite state. Einstein realized in the 1930s that the quantum theory also allows states today called Bell states that imply so-called spooky action at a distance correlations. His 1935 paper was largely ignored, and the clarion call of a new generation of physicists weaned on the quantum theory was, just shut up and calculate. Since it is difficult to see what's going on in an atom, physicists believe that one can ignore these philosophical issues raised by Einstein and simply use the rules of the quantum theory to calculate important and useful data. However, a few remain to take up Einstein's challenge. These pioneers were marginalized early in their careers. How the tables have turned today. Today, superposition, entanglement, and other quantum conundrums are routinely seen in the laboratory. Einstein and John Bell's papers are now one of the more highly cited papers in all of physics. Superposition and entanglement are core components of so-called quantum computers. Their realization could allow a dramatic increase in computing power. Problems they may require several times the age of the universe to process on a conventional classical computer can be tackled by quantum computers. No matter how complex, all computers come down at their most basic level to the processing of simple yes, no, or on-off circuits. In the illustration below, the rearrangement of the head-tail states of ensemble and coils is called a computation. A quantum computer can exploit the superposition principle that disturbed Schrodinger's and others so that the processing of states in which heads and tails appear simultaneously is allowed. This is called quantum parallelism, and it is one of the features that gives quantum computers their remarkable powers. We are now at the very beginning of a newer era in which practical devices exploiting the weirdness of the quantum theory are being introduced to the marketplace. In my opinion, recent advances could bring forth applications that rival the Silicon Revolution. Of course, I think the statement might be overly optimistic if society fails in its commitment to support the curiosity-driven fundamental research. For further reading, several books geared to the general reader are available. They explain in more details the various aspects of the quantum theory touched upon here. For those who wanting a more immersive experience, you can sign up for my undergraduate level course, the first being offered at UNLV on quantum information computing.